Hey guys, it's Mr. Sheeline here. This is going to be the video for the Check Your Understandings when it comes to the 6.2 notes covering the law of universal gravitation. So, looking at Check Your Understanding number 1, I'm going to, read it out, and we're going to solve it. So, Check Your Understanding number 1. Earth's gravitational pull on a spacecraft some distance away is 1.2 times 10 to the second power newtons, or 120 newtons, in magnitude. What will the magnitude of the force of gravity be on a second spacecraft, just 1.5 times the mass of the first spacecraft, and at a distance from Earth's center that is roughly about 0.4 times as great? Okay. So, what we're asked here is that we have this spacecraft that has a magnitude of gravity on them that is equal to 120 newtons. What will the force due to gravity be on a second spacecraft that is 1.5 times the mass of our first spacecraft, but is closer to the Earth? Okay. Now, realistically speaking, this one is just kind of a trick of it's just a puzzle, really. It's a trick where we can just use algebra first, in order to get the units that we need to work with first. So let's just write out what we have and what we don't have. So pretty much all we're given here is that the force of our first object is, I'm just going to put 120 newtons. It's 120 newtons in magnitude, and we're also just given that the mass of our second spaceship is equal to, the mass of our second spaceship here is just, it's 1.5 times the mass of our first spaceship. Okay. Do we need to know the mass of the Earth? Nope, we don't need to know the mass of the Earth, and you'll see that in a second. Okay. What else do we need? Well, we need to know that the radius the radius of our first object here, well, we don't know what that is, but we do know the radius of our second object is going to be just almost half of R1. That's R1, so it's this guy up here. Okay, so this is pretty much all that we're working with here. So let's just write down what we're able to use as far as equations are concerned. So we definitely have this. Okay. In order to get this number, we have to use this. We're going to use this. We would have to use, I should say, this equation. Oh, so we do have G, and G is 6.67 times 10 to the negative 11th power Newton meter squared divided by kilogram squared. Now you'll see though that we don't really need it. And you'll see here in just a second why we don't need it. Okay. So if this were, say, like the force of our first object here, so this is how they found it. They used the mass of the first object and also the mass of the Earth, the radius, the distance between them. That's how they found it. So what we can do is we can just use some little tricks here to try to solve for things that we don't have. Oops, and that's also the first radius. So let's just use this. We're going to use this to solve for, let's say, the radius. So if we were to want to solve for the radius, we're just going to switch R1 with F1. So then it becomes R1 squared is equal to G times 1 times E over F1. We got to get rid of that square. So R1 is going to be equal to G times M1 times ME over F1. Okay. So if we had to solve for the radius between the center of the Earth to our first spacecraft, this is how we would find the radius. Well, we don't have M1, but let's still solve for it. So it's the same way we did here. So using this formula that we just used up here, okay, we did it here. We're also going to use it down here to find M1. So in order to find M1, we've got to just get M1 all by itself. So this is going to be, first I'm going to put this over here. So I'll put M1 is equal to, first I'm going to put this guy, I'm going to multiply my radius of R1 squared to the force of 1, our first object here, and then it's going to be divided by mass of the Earth times big G. Okay, so I would have this equation ready to go if I need to use it for M1. Okay, so I've got these ready to go because I don't know these two. I don't know the radius, I don't know the distance between my first spacecraft and the Earth, to the center of the Earth, and I don't know the mass of the spacecraft. I do know that the radius between the second spacecraft is roughly about half that of the first spacecraft, and I know that the mass of our second spacecraft is about 1.5 times that of our first spacecraft. Okay, so let's write out like F2. Let's write out, let's say if I had to solve for F2, so the gravitational force felt between the second spacecraft and the Earth, it would still look like this. It would be G is equal to M, it would just be M2 times mass of the Earth divided by the radius squared. And this would be R2. Okay. Now let's just plug these things in one at a time. So let's just substitute, just because it's up on top, I want to do that. I'm going to substitute M2 first. So if I were to substitute M2, it would look like this. Because I know that M2 is going to be equal to 1.5 times M1. So first I'll do that. So F2 is going to be equal to G times, and again I'm substituting M2 into this, will be 1.5 times M1 times the mass of the Earth divided by R2 squared. Okay, so far so good. Now I'm going to substitute this guy for what it's equal to, which is the just 0.45 times R1. So then I'm going to substitute that in, so then it'll turn into this, so 1.5 times M1 times ME divided by, it will be 0.45 times R1 squared. Okay. So now I've got something a little different, something to work with a little bit. I've got more numbers here. Okay, now I'm going to do the same thing I did last time. I'm going to just start up here and I'm going to substitute this out for what we just solved for. I'm going to substitute out for this and just see what we're working with. So F2 is going to be equal to big G times, will be 1.5 times this big old boy, R1 squared times F1 divided by ME times big G, all this divided by big G, and then times ME over 0.45 times R1 squared. Okay, so what did I just do? So we left off here. We substituted the M2 for 1.5 times M1, and we substituted R2 for 0.45 times R1. Okay, and then here I substituted M1 for R1 squared times F1 divided by ME divided by G. Okay, now I don't want to go any further because I want to see what we can do here. Let's see what we can do. So if I'm looking at this, this is a denominator, so ultimately this would just be thrown down here anyway. So looks like I can actually start canceling things out already. ME divided by ME is going to just be 1, so we can get rid of that. G and G will cancel out. And what's actually really cool about this we can factor in. So this would just be, if we factored that in, it would be R1 squared times 0.45 squared. Okay. And so why would I do that? Well, look at this. R1 squared divided by R1 squared. That gets rid of that. Okay, so now let's see what I'm left with. I'm now left with F2 is equal to 1.5 times F1 divided by 0.45 squared. So we just went from this monstrosity right here to something we can actually work with. Now, then the question has to be, well, Mr. Sheline, why didn't we solve for for R1, why didn't we put in R1? So we definitely could have. I'll tell you that it would have made it 5 times as hard to cancel everything out. So that's why that's why you go, like, you substitute one in at a time and just kind of take a break, take a look at what you're working with and see if there's anything that can cancel out. And lucky for us, we were able to cancel out pretty much everything just with substituting M1 for this whole mess up here. And we were able to get rid of R1 or R1 squared in the process. And so we were then left with this little equation here. The force of gravity felt between the second spaceship and the Earth is going to be equal to 1.5 times F1 divided by 0.45 squared. Okay, so let's just then fill in what's missing. So it's going to be F2 is equal to 1.5 times F1, which is going to be just 120, divided by 0.45 squared. Okay, and once we pop that into our calculator, what we should get, roughly speaking, is something like 888 newtons worth of force being felt between, again, the second spaceship and the first spaceship. So really, was this a math problem? Not really. It was a puzzle. Okay, it was simply just a puzzle where we first substituted what we had. Our M2 we knew was the mass of our second object, our second spaceship was going to be that of 1.5 times the mass of the first spaceship. We didn't know R1. We didn't know R1, but we knew that R2 was going to be just roughly half, 0.45 times that of, my goodness, that of the distance between our first spaceship and the center of the Earth. We knew G, but we didn't need to use it because it canceled out. And we knew the force of gravity between the Earth and our first object, which was 120 newtons. Okay, and we were able to substitute here. We were able to first solve for the radius of our first object, mass of our first object, and use one of these two. In this case, we used mass because it was a little easier, arguably. We used that in order to solve or to replace a couple of values, a couple of variables, so that we could then cancel them out right here. And then to see that all that was left was going to be 1.5 times F1 divided by 0.45 squared. Okay. And then ultimately we then plug in the correct number here, and then we are able to figure out that the force of the second object is going to be equal to roughly about 888 newtons or 890 newtons, whatever you want your sig figs to be. Okay, so that is check your understanding number one. Just a way to kind of look at, that gravitational, the universal gravitation equation, and kind of make it into, again, a puzzle more than it is a actual problem. So check your understanding number two is much more straightforward. Determine the magnitude of the force of attraction between two uniform metal balls, both having a mass of 4 kilograms, used in women's shot put when centers are separated by roughly about 45 centimeters. So it looks like we've got mass of our first object, which is going to be 4 kilograms. We have the mass of our second object, which again is 4 kilograms. We have the radius between them, which is 45 centimeters, which we'll have to change here in just a bit. And we also have G, the universal constant, which is 6.67 times 10 to the negative 11th Newton meter squared divided by kilograms squared. And we're trying to find F. We're trying to find the gravitational force between them. Now before we can solve that, let's first change this guy. So it's not going to be 45 centimeters, it's going to be 0.45 meters. These are in kilograms, this is fine. I think we're ready to go with basically solving for this. So the equation is going to be F is equal to big G times M1 times M2 divided by R squared. And we can just plug and chug here. So F is going to be equal to, oops, and I don't really want to put it here, I want to put it over here. F is going to be equal to 6.67 times 10 to the negative 11th power times M1, which is 4, times M2, which is also 4, divided by here the radius squared, which is going to be 0.45 squared. Okay. And then once that's all said and done, my answer is going to be F is equal to 5.27 times 10 to the negative 9th power newtons worth of force between those two little shot puts. Okay. Nice. So there's our answer for check your understanding number 2. Again, much more straightforward. Oh boy, look at all this chemistry stuff I didn't throw away. All right, check your understanding number 3. Where'd you go? There it is. So the Hubble telescope follows an essentially circular orbit at an average altitude of 598 kilometers above the surface of the Earth. And then it gives us a couple of variables, some stuff we'll need. Determine the speed needed for the Hubble Space Telescope to maintain its orbit. And we need to express this both in meters per second and also kilometers per hour. So we're given a couple things. So we're given here how to write this down. Let's just say that this is, we'll say that this is distance from surface to the HST. That's 598 kilometers. And then the radius of Earth is going to be 6.38 times 10 to the 6 meters. We're also given the mass of the Earth, 5.98 times 10 to the 24th kilograms. And then we are also given big G, which is 6.67 times 10 to the negative 11th Newton meters squared divided by kilograms squared. Okay. And what we've got to figure out is V. What's our tangential velocity? So the first thing that we should do is that we should recognize this 598 kilometers, and this is distance from the surface to the Hubble telescope. Really, we should have this in meters, so 598,000 meters is what that would come out to be. And not only that, we have to remember, this is from center of mass to center of mass. So if this is the Earth, this is the Hubble telescope, we have to go from, here, better, easier to do it like this. Have to go from the center mass of the Earth to the center mass of the Hubble telescope, so it's going to be like this. Okay, this is our radius. It's not going to be from here, it's not from here to here or here to here. Okay, it's from center of mass of Earth, center of mass of our Hubble telescope. So really it's going to be this 598,000 meters plus this 6.38 times 10 to the 6th power meters. So let's just quick kind of add those up. So it's going to be 6.38 times 10 to the 6th power meters plus really just 5,000 or 5.98, what is that? 1, 2, 3, 4, 5 times 10 to the 5th power meters, which is going to give us here, what is that? Dun, 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 dun. Oops, not multiplied by, but added 5.98 times 10 to the 5th power. So that's going to give us somewhere like, I'm just going to actually write out the whole thing, 7, 5, 7, 8, 1, 2, 3. So it's about 7 million meters. Oops. It's about 7 million meters, 7,578,000 meters from the center of the Earth to the center of the Hubble telescope. Okay, so that's our R. So now we've got R. Now we have to ask ourselves, well, the question is asking about the velocity of the Hubble telescope. Okay, and if we notice, we're not given the mass of the Hubble telescope, so that should tell us something here. And what that should tell us is that the mass of the Hubble telescope really doesn't matter. And so what really matters, though, is, and it's also, they gave it to us, so that should indicate something to us. Really, the mass of the Earth is about the only mass that really matters here. The mass of the Earth is going to far outweigh, literally and also figuratively here, the mass of the Hubble telescope out in space. So what equation do we use? Well, it's going to be that combination of equation that we talked about in the notes. It's going to be v. The velocity is equal to big G times the mass of the Earth divided by the distance between the center of mass of the Earth to the center of the mass of the Hubble telescope. Okay. That's what we're going to use. So let's go ahead and just plug in what we need to. So V is going to be equal to the square root of 6.67 times 10 to the negative 11th power times the mass of the Earth, which is 5.98 times 10 to the 24th kilograms, all divided by the radius. And the radius that we found was the 7,578,000 meters. Okay. And when we pop that into our calculator, this is what we should get out initially. We should get 7,560 something. So really quick, just kind of thinking about thinking about all of the units, it's going to be V is equal to the square root of Newton meters squared by divided by kilograms squared. Okay, for big G, and then 5.98 times 10, that's going to be kilograms, divided by the radius, which is in meters. Okay. So right off the bat, oh, and we can also substitute, remember, newtons. What are newtons? Well, newtons are just kilograms by meters per second squared. So it's really meters per second squared times meters squared divided by kilograms squared times kilograms divided by just meters. Okay. So if we were to organize that a little bit better, it would turn into this. It would turn into kilograms by meters, second squared meters times kilograms squared. And let's see, that would get rid of, here I've got to take some time, so that would get rid of that up top. These won't cancel out just yet. Just I'm putting this together in my brain. Those are taken care of. This would still be up top. That's been taken down, and then kilograms. Okay. So we should probably see that, well, this and this is going to be kilograms squared, so this would just cancel out that. Okay. This would cancel out this, and so what we would be left with here is going to be meters squared divided by second squared. Well, this square root would come in and we'd go blah, blah, get rid of all those squares, and what we'd be left with is meters divided by seconds. Like this would, and then this would get rid of, and we'd be left with meters per second. So ultimately, the velocity here clearly is going to be in meters per second. So just in case you're like, well, how do I know exactly? Well, you don't have to know exactly. This is how you would figure out exactly, but as long as we are putting in the correct units, which making sure that we're using meters instead of kilometers, we're using kilograms instead of like say megagrams or anything larger than kilograms. We're using kilograms, we're using meters, we're using the correct value for big G. We should be good. We should end up with meters per second here. So we've got meters per second, 7,560 meters per second, but we also need to put this in kilometers per hour. So it's going to be this per second. So first I want to change my meters to kilometers. So in every kilometer there's 1,000 meters. Okay, those will cancel out and I'd be left with kilometers. Need to convert seconds to hours. Well, in every 1 hour, there's 3,600 seconds. And then I would solve for that, and I would be left with, specifically, I'd be left with 27,216 kilometers per hour. So here are your answers for check your understanding number 3. This is how quickly our satellite has to orbit in order to stay at this distance, basically. Or else it would be launched into space, or it would be launched into space, or it would plummet to the Earth and burn in its atmosphere. And then check your understanding number 4. Check your understanding number 4 should be pretty straightforward because this is something that is now review. So check your understanding number 4. We have a cylindrical spacecraft traveling to Mars with an interior diameter of 3.24 kilometers. And the craft rotates on its axis at a rate required to give the astronauts inside along the interior wall an apparent weight equal to the magnitude of the earthbound weight. So we have to figure out the speed of the astronauts relative to the center of the spacecraft. So what's the tangential speed? And then what's the period of the rotation? Okay, not the frequency, the period. So here's what we're given. We're given diameter, which is 3.24 kilometers. Okay, and that's pretty much what they give us as far as numbers are concerned. But we also know that the centripetal acceleration needs to be 9.8 meters per second squared. Okay, and we know that because it says that we want to have some sort of the acceleration. Oh my goodness, the centripetal acceleration needs to be somewhat equal to that of Earth's, and so it has to be 9.8 meters per second squared. Okay. Now, what do we need to do? Well, we need to get rid of diameter. We don't need diameter. We need radius, and so we all know that diameter is just from here to here, right? But we want it's from here to here, but we want from here to here. We want the radius. So it's just going to be 3.24 divided by 2, which is going to make our radius 1.62 kilometers. But I don't want kilometers, I want meters, so we're going to go 1, 2, 3. So it looks like my radius is actually 1,620 meters. Okay. All right, so what am I looking for? Well, I'm looking for here V. I don't know V and I don't know T, and I'm trying to find both of them. Okay. So, but I do know some equations in order to get V, and I know an equation to get T as well. So I know that the centripetal acceleration is going to be equal to the tangential velocity squared divided by the radius. So I'm just going to solve for my velocity. Let's just do that first. So that's going to make it to this. Centripetal acceleration times my radius squared. Okay, or the square root, sorry, the square root of my acceleration, centripetal acceleration times the radius. So that's going to turn into 9.8 times 1620. Now we see that the velocity that the astronauts are feeling there on the outside is going to be 126 meters per second, which is pretty quick. Now they won't feel it being that fast, obviously, but you know, it's enough to make it seem like they're walking around on Earth. Okay, well, let's now then figure out, well, what's my period? Well, I got to figure out what T is. Well, I still have my centripetal acceleration at 9.8 meters per second squared. I still have a radius here of 1,620 meters. What's my T? Oh, sorry, got that up there. Well, in order to find T, I know that I've got this equation. Centripetal acceleration is equal to 4 pi squared times the radius divided by T squared. So if I got to find T, I just switch AC with T squared, but then I got to find the square root, so it's going to be T is equal to the square root of 4 pi squared times R over AC. Plug and chug. T is equal to the square root of 4 pi squared times 1620 divided by 9.8. And what I should get for my period here is that this bad boy takes a whole 80.8 seconds to make one full revolution, which is actually pretty quick. That's actually pretty quick if you think about it. So roughly it takes just a little over or just under a minute and a half in order for the entire spaceship, the spacecraft, to make one full revolution. So it'd be quite noticeable actually if like you were looking out a window, and that's something to actually seriously consider. and something to think about when we think about that like luxury. When we think about that one luxury spacecraft, rotating spacecraft here, they made it so that the individuals on there were experience somewhat of a gravity that of the moon's. In this case, it's the Earth's, and the difference is that the Earth, based upon this radius, has to go pretty quick. So if you look out a window on this one, you may feel a little sick. Where the one that they are actually developing, you're going to have the gravity of the moon, but the benefit is that the tangential velocity that the spaceship is moving at isn't as great. So there's less of an actual force being felt. If you look out a window, you're not going to be puking your guts out, presumably, because maybe you won't feel as dizzy because the spacecraft won't be moving as quickly. Okay, and that's really the key to figuring out what that sweet spot is. How big of a spacecraft do we want to make? How much resource is that going to use up, both monetarily and actually physically? And then what speed do we need to have it moving at in order for us to make a particular kind of gravity, so we can keep people comfortable, so we can keep people relatively healthy? Because remember, a lack of gravity is ample environment and opportunity for an individual to lose muscle mass, to lose bone density, to have their heart and their kidneys kind of not explode, but kind of increase in size due to a higher demand to pump out blood and circulate blood. So that's it for the Check Your Understandings, guys. If you still have any questions for me, make sure you ask. But that is it. I'll see you in the next one.